Okay, thank you, Mead. Yeah, we're mostly waiting for our St. Andrews students to come in at this point and join the class. It's great to see so many guests here. Okay, well, why don't I begin? And hopefully we get a few more people joining us as we go. So welcome. I know this is an exciting time for a lot of you that are deciding about choosing schools. And what we're hoping to do tonight is give you sort of a taste of what it's like to be in one of our honors geometry sections. So this is a section of freshmen and sophomores, or third and fourth formers, as we call them here at St. Andrews. And so several of the students in this course are new to the school this year, and a few of them have been at St. Andrews now for 2 years. We're going to get started by hearing from some students present some student work. And feel free to ask questions if you have any. Feel free to interject as much as you need to. And that goes for the visitors as well as my own students. We want to make sure that this is a good experience for everybody. So I'm going to start by sharing some student work with everyone. I'm going to try to stick the file that I'm using in the chat. So if you just bear with me for 1 minute here. Actually, you know what? This is going to take me longer than I think. I don't think we need that. So we'll just go going, and I'll share the file so everyone can see what we're working with. While I'm doing this, just to quickly introduce myself. My name is John Tower. I'm a math teacher here. And I've been at St. Andrews for 13 years. So I've had the experience and the opportunity to teach many different courses here, all the way from honors geometry, all the way up, actually even below honors geometry, I've taught some algebra, all the way up to sort of our most advanced calculus and independent courses beyond that. So, all right. So we're going to start with a couple of student presentations of work, and we're going to hear 4 problems from students. These are problems that they worked on in our last class meeting and spent some time working on together in small groups. So I haven't been a major part of designing these solutions. These are student solutions that you're about to hear. And one of the important things that we do at St. Andrews is not only do we learn how to do the math, but we learn how to communicate the math. And so this is one of the ways that we do that, by doing presentations for the rest of the class. So why don't we start with problem 369 here. And I'm not sure who's presenting, but I'm going to turn the microphone over to someone else.
Yeah, so this is my problem. So the problem was asking, we had a regular pentagon, and if you see, there's segment AC and ED, and we had to prove that they were parallel. So how I did this is I divided 540 by 5. Because it's a regular pentagon, there are all equal angles. So I knew that the exterior angle was 108 degrees for segment AC. The interior angle, and then the other interior angle was also 108 degrees for ED, because those are both angles A and angle C. And then because a straight line has 180 degrees, I subtracted 180 from 108 and got 72. And so I knew that the other outer area The other interior angle was 72 degrees, and then the other one was also 72. So because both of the, sorry, that would connect. I meant the other one,
Oh, sorry.
like on the other side. That's okay.
Can you give me a name for it? What's the name of the angle you're talking about?
The other interior angle
The one,
on E and A.
E and A.
So they create a 180-degree angle.
Oh, I got you. Okay. So this one?
Yes.
Okay. Mhm.
So because they both have the same interior angles and they're both drawn from a similar angle, they would be parallel because they wouldn't ever cross.
Which lines are parallel?
AC and ED.
AC. Okay. So that's this line right here and ED.
Yes.
All right. Okay, so commentary or critique from the class? Did we follow that? Did that seem to make sense?
So far, yeah.
Yeah. Okay, and one of the other parts of this question was to find the measures of, I think it was triangle ABC, right? To find the interior measures, and it looks like you have those right here, 36 degrees, and this would also be a 36 degrees, right? The two green angles. And why would those both be the same? Why would those both be 36 degrees?
Is it because it's an isosceles triangle?
Yes, right. Those are the base angles of the isosceles triangle ABC. Okay, very good. Any other comments on this? All right, let's move on to our next problem, which looks like a proof. So one thing, I'm not sure who's presenting this one, but could you just read the problem so that we all hear it out loud once before you start talking about it?
Okay, so the problem says, given square ABCD, let P and Q be the points outside the square that make triangles CDP and BCQ equilateral. Prove that triangle APQ is also equilateral. So first we drew the picture of the square and the two equilateral triangles. And then we noticed that it looked like there were three isosceles triangles that included the line AP, PQ, and QA in it.
Say that again. I'm sorry, I missed the.
Like I just kind of took out the extra lines in the middle, so it would look the picture
okay.
neater on the inside. And then if my other partner wants to talk about the statement and proof.
And then we also said that when we connected, I think it's A to Q, A to P, they create equilateral triangles. And also P to Q, and then we put that into our statements and our reasonings. So we said that ADDP, PC, CQ, QB and BA all equal each other because it's given. And then we said that measure of angle B equals 90 degrees plus 60 degrees because B and D each encompass one right angle in the square and one in the equilateral triangles. And then measure of angle D is equal to 90 degrees plus 60 degrees. I think it's for the same reasoning. And then measure of angle C has to equal 360 degrees minus 90 degrees minus 60 degrees minus 60 degrees. And we weren't really sure how to put this into a reasoning, but we just kind of like described what our thought process was in 4. We just kind of thought
Yeah,
that
I think that's just arithmetic, right? I mean, that's what you're saying there is you're looking at some of the known angles and you're subtracting them from 360 degrees
yes.
to find the remainder of it. Sure. Yeah, I like that. Mhm.
Yes. Yeah, and our other partner wants to go. I can just keep going.
Yeah,
but-
Devin, I appreciate it. I'm not sure who else is going to pick that up.
Yeah. And then we said that measure of angle B, measure of angle D, and measure of angle C are all equal to each other due to substitution.
Mhm.
And then we said that triangle ADP and triangle PCQ and triangle QBA are all equal to each other due to side angle side triangle congruency theorem.
Right. And so those are the 3 small exterior triangles, right? On the outside of the figure. Is that what you're talking about?
Yes.
Good. Okay. Yeah.
And then our last statement says that segment AP, PQ, and QA are all equal to each other due to CPCTC.
Yes, which we love to say, right? Our favorite thing, CPCTC.
Yeah.
Okay. So I like it, right? And this is a good example of taking a figure that we've drawn and sort of extrapolating some information from it and creating what's called a formal proof, right? So terrific. How does everybody else, are there any critiques of it? Do you have your hand up or are you just stretching there?
I was just stretching, but I would say, I don't know if they said this, but the third angle theorem would also be a good thing to put into proof to show that the triangles were isosceles and also show that the square had a fourth angle that was congruent, which would then make all the figures equilateral. So then you could prove that a little bit quicker and better, I think.
Yeah, there are many ways to prove these. And so this is just one of them. I like it, right? That's enough to show that we have an equilateral triangle if the 3 side lengths are congruent. Great. Okay, so let's look at the next problem. Which is 371.
I'm sorry, you want me to read off the problem first, right?
Yeah, that'd be great.
All right, so 371 says the sides of an equilateral triangle are 12 centimeters long. How long is an altitude of this triangle? What are the angles of a right triangle created by drawing an altitude? How does the short side of this right triangle compare with the other 2 sides? So Griffin and I were tackling this problem, and what we first did was kind of draw an equilateral triangle matching the description on a bit of a coordinate axis. So since it's an equilateral triangle, they have all the same side measurements and also angle measurements. So we drew each side having a length of 12 units, and then each angle measurement being 60 degrees. Since triangle has total of 180, there's 3 angles in it. So 180 divided by 3 would be 60. And then for finding the length of the altitude, we figured that since, well, as you can see in the drawing, the x value of the point, I guess, upwards would have to be in the middle of the left and right points. So in this instance, we started at the origin, so 0, 0, and then 12, 0. The third point would have to have its x value as 6. Otherwise, otherwise the other lengths would be kind of lopsided, so it wouldn't be equal. And since creating an altitude or the line of altitude makes a right angle with the baseline selected, we can actually use the Pythagorean theorem of a squared plus b squared equals c squared, except we already have the hypotenuse of 12, and then we also have one of the side lengths of 6. So we can actually just put 6 into A and then 12 into C, which gets 36 plus B squared equals 144. Subtract 36 from both sides. B squared equals 108. You find the root of both of those to get B equals the square root of 108, which putting into the calculator is approximately 10.39 units, which would be the altitude. And then what else? Oh yeah, also in terms of finding the angles of the right triangle created by making this altitude, we already established that the altitude aligned with the baseline creates 90 degrees, so we already have that. Also, if we're looking at the right triangle that you kind of drew, the angle on the right side wasn't tampered with, so it's still 60 degrees. And then the one up top, since it was split in half from the other 60-degree angle, that would be 30.
Great. Thank you, Miguel. So I want to build off of this a little bit. The other class also got the square root of 108. But one person in the other class said, what if we took that square root of 108 and wrote it in what's called simplest radical form? So what I mean by that is, how do we reduce the square root of 108 into its simplest form that includes the radical? And one thing you might recognize is that 108 is 36 times 3, which means that this value of B that we're calling the altitude could be rewritten as 6 times the square root of 3. Does everybody see what I'm doing there? Now, this seems to me that there's some sort of pattern going on here, right? I'm seeing side lengths of this triangle that are in proportion of 6 is one of the side lengths to 6 root 3, which is another side length we just found, to 12. And I guess my next question would be, what if instead of saying we start with an equilateral triangle of 12, what if we started with one of like 10, side length 10? Would our values, so if the original side length over here was 10, would we get one of the side lengths to be 5 and the other side length to be 5 root 3? Would that be the ordering of the side lengths? What do we think about that?
Yeah, I think yes, because would it just be the x root 3 2x triangle?
Yeah, oh, you already know that one. But right, that's what we're after here, right? So I think what we're seeing, and let me just move this aside so I can draw a little better, is that if we're in a 30, 60, 90 triangle, and the shortest side length is length x, right, 5 or 6 from the above examples, then the hypotenuse length is 2x. And the height or altitude length is going to be given by this same equation that Miguel just solved. So height squared equals really 4x squared minus x squared, which would be 3x squareds. Or height would be the square root of 3 times x squared, which is the square root of 3 times an x. So, conclusion, in a 30, 60, 90 triangle, and when I say in a 30, 60, 90 triangle, I mean in any 30, 60, 90 triangle, the side lengths of the triangle are in proportion x to x root 3 to 2x. So if we know the shortest side length is 3, we know the other leg length would be 3 root 3, and the hypotenuse length would be 6. And this is true for all 30, 60, 90 triangles. Does that sound good? All right. We had one more problem to look at, but since we're running a little low on time, I think we're gonna skip the last student presentation and go on to what we were gonna do next, which was to look at a new problem. So I'm sorry about those of you that prepared 374. We'll take care of that in class next time. But what I'd like to do now is to put you guys into a small group for about 5 or 10 minutes, not 10 minutes, maybe about 5 minutes, some of our students from St. Andrews, some of the visitors, and to talk about this next problem, 375. It's probably worth right now taking a quick screenshot of this so you have the problem in front of you. All right, I'm going to put everybody into a small breakout room and oops, sorry. To work together for just a few minutes. Okay, so we're going to pick about 5 breakout rooms. And I want to make sure we got some people from each. Okay, so will the St. Andrews students please lead the discussion of this problem? And here you're getting an invitation to join a breakout room. So if everyone would please do that. Okay, I think we're all back. And I think that at least what I saw from most of the rooms that I was in was you saw that this picture was very similar to the picture of the problem that we heard number 370. It's a different problem though, right? So this one says, given this square ABCD, right, create these points P and Q so that the two triangles BCQ and DCP are equilateral. And then what? Then it says, let segments AQ and BP. So segment from B to P looks like this, and A to Q looks like this. Let them intersect at some point T. And can you find the measure of angle ATP? So does anybody want to share any thoughts on what they thought of how to get started with this? Or anything we might have known from the previous problem that we looked at?
Okay, so we said that from the previous problem we had that AQP would be a equilateral triangle, right? So if you draw a diagonal from A to P, that's equilateral. And then we Quinn stated that since we know that AB and BQ is isosceles and BQC is equilateral, that angle B will be 90 plus 60.
Okay, agreed, yes. So that angle right there, the green one I just put on there, you're saying is 150 degrees.
Right.
Okay. What else? What is BP doing to the equilateral triangle that we've created?
Well, you also know that the other angles of the angle ABQ would be 15 because there's
Okay.
180 degrees.
Yep.
So that could help you find the angle, one of the angles of triangle TQP, because we know that ABQ, QPC, and APD are all congruent.
Mhm.
So that other angle right there would be 15 degrees. And we know that angle Q as a whole is 90 degrees. Because it's part of the square, I think.
The angle at Q, which can you give me a good name for that one? Because there's several angles that I can see that exist at Q.
Just itself.
So the BQC?
BQP.
BQP, okay.
So from there, we can finish that angle off by subtracting 30 from 90 degrees and getting 60.
Okay, yeah, I'll buy that. That sounds good to me, right? So another way of thinking of that is that the entire angle BQC is 60 degrees, and we're adding in 15 degrees over by the yellow segment QP, and we're subtracting out the 15 degrees to the left of that.
Well,
So
I think,
that-
wouldn't BQP be 75 degrees?
Yes. It would. But I think what we're after is this angle, right? TQP.
Yeah, I was thinking that if we connected QTP together as a triangle, then maybe we would be able to find the other angles and then subtract those two angles from 180 degrees.
Right. Well, isn't this angle TQP 60 degrees?
Yeah.
Based on the result that we had before, that this was an equilateral triangle, AQP. So its interior angle has to be 60. And what could we say about this angle up here? TPQ.
You could say that would wait. Oh, yeah. Couldn't you say that that's 62? Because it's the same triangle over there.
No,
Well, it's half of 60, isn't it?
yeah, so it's 30 degrees because the line TP splits that equal. Yes, splits it in half.
Yeah, right. That's a bisector of the angle. So then what does it make the angle at T, right? PTQ.
Makes it 90.
It makes it 90. Good. Yes. Right. And if that's 90, what's the angle that's adjacent to it?
Also 90.
Also 90. And so the measure of angle ATP is 90 degrees. Good. Okay, I just want to share with you, we're not going to probably have time to do these problems, but I just want to share with you a couple more problems that are coming down the pike, just so that our guests can see sort of what else we're working on. So these are sort of a preview of coming events. So one of the things we've been doing is looking at, getting off of the two-dimensional plane and stop looking at two-dimensional geometric figures, but looking now in three-dimensional space. And so one of the problems we're going to do in our next class is this one, number 384. It says 2 of the corners of this rectangular box, A, B, C, D, E, F, G, H, are located at 2, 1, 3. Well, that means that the X coordinate in 3 space is a 2. The Y coordinate is a 1, right? You guys are all familiar with graphing on a coordinate plane, what it means to graph a point X, Y. But now we're adding a third dimension, a depth dimension. So if we were saying the X component takes us horizontally and the Y component takes us vertically, then the Z component, that 3 of the point A, gives us depth and adds a third dimension. So this problem says, here are 2 points, A and G, that are defined in 3 dimensions. The edges AB and AD are parallel to the X and Y axes. Add in the coordinate axes to the diagram. So we're being asked to identify on our figure where the origin is. Where is 0, 0, 0 going to be located? And after that, how could we draw in the rest of those coordinate axes, right? The x-axis, the y-axis, and the z-axis. And then you can see there's a couple continuation questions that are going to build off of that. We want to find coordinates for all the vertices. We want to find side lengths or edge lengths. We want to find distances to different planes. And the last question says, how could we tell if one of the angles here is a right angle? So this is another sort of subset of problems that we've been working on. We're just starting to, here in, the very beginning of April, we're just starting to look at this type of three-dimensional work. This is sort of more advanced math, I would say. This is, ultimately going to lead us, by the time some of these guys are seniors, they may end up taking a course called multivariable calculus, which is the study of calculus in 3 dimensions. And so these are the very first introductory problems in that journey. So we've been at it for about 40 minutes now. And what I'd like to do is sort of let my students be excused because they have to get to study hall in about 20 minutes. And I'm happy to stay on and answer any questions about the math program or about anything you've seen today with any of the visitors. So if you also don't have any questions, you're free to sign off. Don't feel like you have to stay on. I hope you've enjoyed our short sharing of some of the math that we're doing in our honors geometry class. And we will hopefully look forward to maybe seeing some of you on campus next year. So I'm going to excuse my students now and thank you guys for being here on a Thursday night. I know it's busy time for everybody. And anybody that has any questions for me, you're more than welcome to stay on and ask them.
Thank you.
Thank you.
Welcome.
Hi, my name is Quinn Ferguson. I personally don't have any questions, I don't think. My dad is a math teacher at the Lawrenceville School. Well, he just moved from Lawrenceville School to PDS, I'm sorry. He teaches calculus and pre-calc and stuff like that. So I was gonna call him to say that if he had any questions he could ask you, but he didn't pick up his phone, so
Okay.
he might just email you soon, just asking you some questions.
Yeah, that would be fine. I mean, any of the math teachers you can easily find on the school website.
Great.
And the email addresses are all there. So, and mine's just jtower, so at St. Andrews-DE.
Great. All right. Thank you. It was
You're
fun.
welcome.
Bye.
Bye.
Hi, I'm Finn, but
Hi, Finn.
I just had a question about how we're going to be tested for going to honors geometry. Like, is it solely based off of the
Well, there's a lot of things that get sort of put into it, but some of it is what course you're coming from, right? So we'll look at your transcript and see what courses you've taken.
So I'm in Algebra 2 right
and then
now.
there's a summer placement test that new students take.
Yeah.
Right. So we'll mail you a summer placement test and you'll take that on your own and you'll return it to us and we'll look through it and we'll place students appropriately based on that. If you show up to campus and you realize, and the math teachers really realize this early as well, that you're underplaced or you're overplaced, then we quickly sort of pivot you into the right course.
Yeah.
So, we spend a lot of time thinking about that. I think that's the most important thing for us is to make sure that students are in the appropriate course for them, that they have the appropriate level of challenge, that they're not just, taking a course that they've already took in middle school, or if you're applying as a sophomore that you took last year. So yeah, we're very thoughtful about how we get people into the right courses.
Great. Thank you so much.
You're welcome.
Bye-bye.
Bye.
So my name is Camilo, and I have a question about what would a typical class look like in math?
All right. So the typical class, this is a weird medium to be doing math class in, right? In Zoom. So I was trying to model sort of like what a normal day might look like for us, right? We normally start by hearing from students on the work that they've done before, right? So those problems that you heard at the beginning of class today were all students who had worked on those problems in the previous class, with a little bit of guidance from me, but mostly from each other. And they presented those presentations based on their own homework. So that's normally how we'd start a day. Then we start looking at new problems, and putting you guys into the breakout rooms was sort of a try at doing that. But in class, we usually break up into small groups of 3 or 4 students, and we work on whiteboards for about 20 or 25 minutes on new problems as I or the other teachers walk around and sort of help groups that are stuck or ask specific questions about what they're doing, that sort of stuff. Then the end of the class is sort of what we just did, like a reporting out of the new problems, right? Were there any questions on things that came up? How do we take this knowledge, this sort of brainstorming session that we've had, and now go home and write these problems up a little bit more formally? So that's sort of like the day-to-day of what's happening.
All right. Thank you.
You're welcome.
Hi, I'm Madeline, and I was wondering, currently what my school does is there's Algebra 1 and Algebra 2, and I'm not completely sure I'm right when I'm saying this, but there's only 1 year of algebra at St. Andrews, right?
Well, there is and there isn't. I mean, like, this is a geometry course, but there's a lot of algebra built into it. And so we like to think that there's algebra every year and there's geometry every year. And there's pre-calculus. When you get to pre-calculus as a junior or, sophomore or junior, you're not done with geometry. You're not done with algebra. There's enough review built in, and there's still, you're using those skills to develop new ideas in pre-calculus. So even though we don't necessarily call it algebra 1, geometry, algebra 2, pre-calculus, there's really all of those subsets of math sort of built into each of our courses.
Okay, so it shouldn't be a problem if I've taken like algebra 1 and geometry if I do pre-calc in my freshman year, right?
I can't tell you what you'd end up taking. As I was explaining before, we give you a test. For a lot of students coming here, the way we do the problem solving is new. And so having a little familiarity with some of the course material might be helpful in that. So we might say, you've taken geometry, but we'd like you to take honors geometry here and pick up with that. Or we may say, wow, you've taken all this geometry and your placement tests look great. So there are occasions when freshmen do take pre-calculus, but I can't give you you would definitely take this next year without, looking at some of your work and seeing what you're capable of doing. And as I said before, like, I think the most important thing is not necessarily getting so advanced. It's being in the right class, right? One where you feel like you're really being challenged. And I think there's enough challenge in all of our courses that wherever you get placed, you'd probably feel like this is a good course for me.
Okay, thanks.
You're welcome.
Okay, bye.
All right, goodbye.